Alright, so we have another paradox here. Uh, we it appears that from the Enterprise's point of view, the when it's moving, that the hangar appears too short for the Enterprise to fit inside. But but according to people that are at rest at the hangar, the Enterprise appears shorter and will fit inside just fine. Okay, so the hint to sort of getting out of this paradox is to remember that this first consequence of Einstein's postulates, that is the relativity of simultaneity, and we will get back to this and resolve this once we introduce the proper mathematical transforms. But it's a specific case of a general principle that what often appear to be paradoxes in special relativity in these situations are often, maybe usually, just examples of applying one consequence of Einstein's postulates and ignoring others. And we have to remember that these consequences are a package deal. We have to consider all the consequences for each specific problem, all the consequences which apply for each specific problem. Okay, now that we've introduced Einstein's two postulates of special relativity and have discussed qualitatively the three main consequences of those postulates, let's discuss briefly some early evidence of some of the relativistic effects that follow from these postulates. Okay, in particular, let's focus on this 1941 experiment by Rossi and Hall. They measured the flux of muons. Muons are particles that are like electrons but much heavier. They're charged particles. The flux is the number of particles per unit area per unit time, and they measured this flux in two different places. One on the top of Mount Washington at about 2,000 meters altitude. Mount Washington is in New Hampshire, and they also measured it at the base near sea level. And what they found was that there were many more muons. The flux of muons that they measured at the base was much higher than what they expected to find relative to what they measured at the high altitude at the top of the mountain. Given that the muons don't last very long, that is, they decay into something else in a relatively short amount of time, roughly about 2 microseconds. Okay, so it's important to realize that that muons are, as I said, they're unstable particles. They decay into something else relatively quickly within a couple microseconds, and they're produced, or at least one way to produce them is via interaction between cosmic rays, those high energy particles coming from outer space. When those particles enter the Earth's atmosphere, they interact with atoms and molecules within the Earth's atmosphere, and through those collisions they produce these high energy muons. Now, these muons that are produced in this way travel very, very fast. They travel at close to the speed of light. So before they decay, they can actually travel towards Earth a certain distance. But because their lifetime is quite short, that distance shouldn't be. That distance is still relatively small compared to the thickness of the atmosphere, and very few of them should be left when at the Earth's surface, basically at low altitude. We can do a simple classical calculation to estimate this flux, or how many should remain at the Earth's surface.